Hi, this is a short optional video I'm recording to help out with Project 6. That last project uses unions and enumerated types, and we won't get those till lecture 24. But if you want to get started on the project earlier, this should give you enough information to go ahead and do that. The project uses enumerated types, and C supports the same kind of enumerated type as Java. The C mechanism, I'll go ahead and admit, is a little simpler than what's available in Java, but this is to let you define a type that has a fixed set of values. Like here, I'm pretending we need a type that has colors, red, green, and blue as values. Now, up till today, we probably have done that with the preprocessor, kind of like the code I'm showing here. We could have preprocessor constants for the value red. We could set that to 0. Green, we could use 1 for that. Blue could be another name for 2. And then we could just use an integer value to keep up with which of those we're using. And this works okay, but it may not give you as much help from the compiler as you'd like. The compiler doesn't really know that color here is a special type. It would let it have any integer type. And it doesn't know that these 3 values go with color. Enumerated types, just like in Java, they let us define a type that has a fixed set of values that the compiler knows about. So it might be able to give us more useful debugging help if we make a mistake in our code. The syntax, I think it looks a lot like Java, although it's been a little while since I've done this in Java. It looks a little like the struct syntax in C. You have the keyword enum, and then the name for the enumerated type, and then inside curly brackets, you list as many values as you need. So here I'm defining a new enumerated type that only has 4 values: red, green, blue, and orange. If you want to make an instance of this type, kind of like a struct, you have to use the enum keyword to do that. So I had to say I want to make a new variable of this enumerated type. I want it to be the enumerated type color enum. Here's the name of my variable, and then you can set it to any of the 4 values we defined up above. For enumerated types, once you've made a variable of that type, you can compare it. You could test to see if it equals one of the particular values. You can set it to the enumerated values. You can compare 2 variables that are both of the same enumerated type. Just like struct, you can use type, well, like we just saw, backing up a slide, every time you have to make the enumerated type, you have to use the enum keyword. If you want a short name that you can just use like any other type name, typedef makes it easy to do that. So normally if people were naming an enumerated type or were defining a new enumerated type, they might not even bother giving it a name for the enumeration. They could just typedef that directly to a type name. So usually you'll see this like this. And then direction here, I'm defining a new enumerated type that has directions up, down, left, and right. I'm not even bothering to give a name for the enumeration. I'm just mapping that directly to the type name direction. And then I can use that like any other type name. Enumerated types are trying to do the same thing that you've done with enumerated types in Java, but secretly. They're really just a wrapper for what we were doing back here on this first slide, for having unique integer values for each value of the enumerated type and storing the enumerated type like an integer. And you can see this if you try to do what I'm showing here. You can print out the value of an enumerated type and it'll print like any other integer. You can assign from one of the enumerated values to an integer, and that'll work just fine. So it's really just a thin syntactic decoration for what we started with, a name for a bunch of unique integer values and a type name that we can use to define new variables that are storing those integer values. If you want to have control of those integer values, you can do it. When you define a new enumerated type, by default, it starts giving out values from 0. So whatever the first value you specify is, it gets the value 0 and then 1 and then 2. But you can use a syntax like this to say what you want. So here, instead of happy, so I'm defining a enumerated type for kind of your mood, if you're happy or sad. Happy as the first one would get 0 if I didn't say anything else, but this equals 2 says started out with a value of 2. So happy will just be another name for 2 as far as this enumerated type is concerned. I didn't say anything for the next value, so it'll just continue from the previous value. So afraid will get a value of 3. For bored, I said I want you to go back to 0. And then after that, it'll start counting up from there. So blue will be get a value of 1. Glad will get a value of 2, which is really another name for the same thing we had with happy. C doesn't prevent that. If you want 2 different names for the same enumerated value, you can do that. It's just those will always compare the same way. So defined this way, I really can't tell the difference between happy and glad. Enumerated values, since they're secretly just stored as integers, you can use the normal integer operations on them if you want. So here I start out a mood with happy, that's another word for 2, and then I add 1 to it. Looking back at the type, that would increment it to whatever value afraid represents, 3. And then I increment it again, and then it doesn't match any of these values. Enumerated types in C don't guard against that. They're, like I've said a couple of times, they're really just a wrapper around an integer value. And if you increment it past any of these legitimate values, it can still store that. It just won't match any of these names here. The values of enumerated, or the values in an enumerated type, obey the same scoping rules as variables, which means you can have 2 different enumerations with the same value, just not at the same scope. So I could define a color enumeration that had red, green, blue, and orange, and I could define mood that had happy, bored, afraid, and blue, but just not at the same scope. The compiler would say, well, if you say the word blue, I don't know if you mean the one defined in this enumeration or the one defined up here. If you define them in different scopes, like I'm doing down here at the bottom, the compiler's perfectly happy with that. If you write code down in this after this second enumeration, since that's the one with the more narrow scope, if you say blue, it'll assume you mean this blue rather than this one. But if you define them at the same scope like this, the compiler's not going to be happy about that. So enumerated types are normally used for defining elements of an enumeration, but there is one trick you can do. And I don't think we'll use this semester, but you will sometimes see this used by other people. And it's a technique to use enumerated values as a quick way of defining constants, but constants that respect the normal scoping rules. Here I've got a struct, and it's got 2 arrays, and here I'm pretending they're both the same size. They've both got room for a string of 99 characters. It's a little, if they're both a standard length, it's a little unfortunate to repeat the same constant there. We'd normally call that a magic number. I could use the preprocessor to define this constant, and that's what we've done this semester. That's what we'll continue to do this semester. But a problem with preprocessor constants is they don't respect scoping rules. So if you define a constant like size with a value of 100, no one else can use that name. You kind of took that name, and if someone else tried to define a constant with that name, the preprocessor would complain. A constant that respected the scoping rules would be nice, and even though it's not intended to do that, some people will do that with the enumerated type. Since an enumerated value lets you pick whatever you want it to evaluate to. So here I'm making an enumeration, I'm filling in a value size, and I'm choosing 100 as its value. I can pick that to represent any value I want. And I didn't say this before, but enumerated values are considered uh, constant expressions. They're considered compile time constants. So you can use them wherever a compile time constant is expected. You could use them as the size of a global variable. You could use them as the values on cases of a switch statement. So you will sometimes see people use this as an alternative way of defining constants, but one that's nice because it can go in and out of scope. So you could define a struct that used a constant, but a constant that was only defined within that struct. This is probably more useful in C++ than it is in C, because C++ gives you more mechanisms for talking about the scope of names. But this still can be a handy in some cases if you're writing C code. So we just learned about enumerations, kind of a language feature that we've gotten by without up till this point. Another language feature is the union. I think the right way to think about a union is, starting with the idea of a struct. With a struct, you can define something that has multiple fields, like I'm doing here, and the fields get laid out in memory, you already know, one after another. The struct reserves space for each of the fields, possibly with some padding in between. A union is kind of like that, but instead of leaving separate space for each of the fields, it lays out the fields so they each use the same space. Now, why would you want to do that? Well, a union lets you define a region of memory where you can choose how it's used. You could choose, so here I've got a union that can store, I'm pretending it's an email address, a character string of up to 24 characters, or a phone number. Maybe that I want to store as 3 short values, little integers, or maybe GPS coordinates. And maybe I want to store those as 3 floating point values as doubles. But I don't need all of them at the same time. I just need any one of those. The union lets me do that. I can say these 3 fields, and by putting them in a union, the compiler implements that union. So each of them occupy the same memory. So I can have either an email address or a phone number or GPS coordinates, just not all of them at the same time. Like I've tried to show in the picture, it uses the same memory to store each of those. So whereas the size of a struct would be the size of each of the fields, maybe along with some padding, the size of a union would be the size of its largest field. It has to plan to be able to store either this 25 character array or this, I guess it'd be a 6-byte phone number, or I guess these would be 8 bytes apiece. So for 2 doubles, that would be 16 bytes for global coordinates. So it seems like here email is the largest field, so that would determine the size of the union. The union has to be able to store any one of its fields, so it has to have enough memory for the largest of those fields. Normally, the way you'd use a union is to handle variations in the data you want to store. And that's kind of why I picked this example. Maybe you want to be able to store contact information for a person, and you need either a phone number or a email address, or I just had to make up another example. So I picked GPS coordinates, where the person is. So here I made so to show off an example of this, I made a union, an instance of this union called Bill. And then I used the phone number for Bill. And then I made another instance of the union called Mary. And for her, I used the email address. If I want to print these out, well, for Bill, I can get the 3 components of Bill's phone number. For Mary, I can print out her email address as a string. But it's up to me to remember which of those fields I used. If I take Mary, where I stored a phone number, but then I stored an email address, but then I try to access her phone number, I'm going to be looking at the same memory, but it's going to be memory that was set as if it was a string, and now I'm accessing it as if it was an array of 3 shorts. So really, it's probably going to look like garbage if I take something that was set as one big string and try to look at it as if it was 3 short variables, or sorry, 3 short integers. So this last printout would probably print out garbage. Where would you need a union? Well, normally a union is used as just part of a struct. Maybe you've got a struct and you've got some things you need to store, like if you were storing contact information, you might build a struct that held the name of the person you wanted contact information for. And then if you wanted to know how to contact them, you might store a union like we were just talking about, either their email address or their phone number or their GPS coordinates, but maybe you only need one of those. So you use a union for that, like we were just looking on the previous slide. Now, since the union lets you store any one of those, you need to, it's up to you to remember which one you stored. So did you store phone number for a particular person or GPS coordinates for a particular person? Since you have to remember that, you're probably going to need another field to keep up with which of those parts of the unions you used. And that's often a good job for an enumerated type. Here between the name field that everyone has and the union field where, well, everyone has one of those values, I've got an enumeration that keeps up with which one I stored. I called it type, and type is either email address, phone number, or global coordinates. And that's just an enumerated type that reminds me of which part of the union I'm using. And then if I wanted to make a whole list of contact information, I could make an array of this object. Each person could have a name. Each person lets me use one of the fields of these unions, but I can set the type to remind me of which field I'm using. So for Mary, if I'm storing her email address, I'll fill in the type with email, this first member of the enumerated type, so I remember which of those fields I'm using. And then here, like if I made a whole array of contact information, and if I wanted to go print it out, I could go through each element of the array, but then to print it out correctly, I might need to look at that type field and say, oh, if for this person you're storing the phone number, let's print it out like a phone number. Or if you're storing the email address for this person, let's print it out like an email address. So often unions are going to be used along with enumerated types. The union will let me store one of a number of values, and the enumerated type can let me remember which of those values I'm using. We already said for unions, well, you might use a type def to map the union name to a short type name, so you don't have to keep saying the word union over and over again. But often, if unions are defined in a structure, you won't even bother giving them a type name. Maybe you've got, well, for the example we've been using, maybe email or phone or global coordinates, maybe that's only something that I use inside the structure. So I could just define the union inside the structure like I'm doing. I've got contact information and it's got a name field and a type field and a union. And I didn't even bother giving the union a name. I just said, well, a union's got an email address or a phone number or global coordinates, and just call that field info, but don't even bother giving a name for the type. The only place you're going to use that field is info. And then, kind of like backing up a couple of slides, that's kind of what I did here. If you want to get an element of your array of contacts and you want to get the phone number part of that, well, that's contacts, whichever element you want, the info field, and then the phone number part of the union. So just defining the union inside the struct and not even bothering to give a name for the type usually works just fine. It's a little Inconvenient though, because every time you talk about the union, you have to give the name of that field. Backing up a couple of slides, right here, if I want to talk about the phone number, well, that's really part of the union that I called info in this struct. And that info field is part of one element of this contact array. So whenever I want to talk about, at least backing up a slide, one more slide, whenever I want to talk about contact info, I have to talk about this info field. And that makes addressing the parts of the union a little bit longer, which is why in newer versions of the standard C99 and in the GNU version that we're using, even GNU's C11 standard permits this, but even the GNU C99 standard lets you do it. It lets you define what's called an anonymous union. This code is the same as what we looked at a couple of slides ago. I've got a union defined as part of this struct, but I didn't even bother to give it a field name. Older versions of the language didn't let you do that, but as of the C11 standard, or like I said, C99, if you're compiling with GCC, will let you define a union as long as it's part of a struct. You don't even have to give it a field name. And then you can refer to the fields of the union, like email or phone or coordinates, as if they're fields of the struct, but they still all share the same memory. So in this struct, you can treat it as if it has a .email field or a .phone field or a .coords field. You just can't use all those fields at once because they all share the same memory. We got a little more stuff to talk about, but this covers enough to let you do our last project. It uses a little bit of enumerated types and unions. So hopefully, if you want, this will let you get a head start on that. Good luck on the project.